So check this out. So if psi 1, for example, of x and t is equal to psi 1 of x times e to the minus I omega t, then psi 1 of x and t complex conjugate times psi 1 of x and t. So the complex conjugate, what's going to happen, and you can fill in the details, you just write this out, this is going to be psi of x, psi of x, star psi of x, where these are the time-independent answers from earlier. So what this is saying is that it looks like the probability, while it is a function of position in general, its probability is a function of x, it is not a function of time, no longer time-dependent. The probability density, that's what the wave functions are. The wave functions are time-dependent, but the probability is the probability is not time dependent, is the idea. Let me point out a place in the textbook that I think stuff starts to get super interesting. So all those things that I was just describing are happening in your book right around in here. It's not a lot of stuff. Here is Euler's formula. Here is the application of the time dependence. Here are the right-moving and left-moving wave parts of both the region 0 and region 1 wave functions. But the really cool part is really these drawings. And these drawings depend on some choices that are made on the following page. On the following page is a really interesting discussion. This stuff is super cool and interesting and important. It talks about the coefficients a prime, b prime, c prime, d prime as intensities or as amplitudes. They're the brightnesses. It's kind of a weird way to talk about it, but it's kind of like in the language of thinking about light waves. Of course, we're talking about a quantum single particle. Yeah, but anyways, they make the argument just based on, thinking as physicists, not as mathematicians, but if d prime represents a particular intensity, then maybe they would have reason to argue that there could be an experiment where that experiment matches this modeling effort by stating that the model has that parameter of value 0. I'd love for you to read this. Why is d prime being selected or chosen as 0? Like, what does that model? And then why do those choices give rise to these pictures? These pictures are really interesting, and what you should do is try to figure out. So picture on the left is t equals to 0, and the picture on the right is t a little bit later in time. The probability picture, the psi squared, this is psi star psi, does not change in time. You can see that this peak goes down to a trough, back up to a peak, and then it levels off and stays constant. And that's exactly the same for a short amount of time later. There is no time dependence in the probability. But if you go down and look here, what's really cool is they split the wave function into real and imaginary parts. I alluded to that in the discussion just a second ago. But the solid line is the real part, and the dotted line is the imaginary part. You'll notice that the solid line, the amplitude on the left-hand side shrank, and the dashed line, the imaginary part, the amplitude grew. So you can see that there's in some sense that e to the minus I omega t is the reason why we're seeing some really interesting amplitude switch off. But not only that, like, look at this. Here is, say, the peak of the solid line, the real part. It's sort of one wavelength away from the barrier, or at least the step. And then a little bit later in time, can you see that actually that peak has advanced over a little bit towards the right? And that advancement of the peak indicates that there is some traveling nature. The dashed line did the same thing. In the other side, this is above the step, on the right-hand side of the step. You can see that there is a traveling nature to the real and imaginary parts, but notice that their amplitudes don't change. And if you can figure out why the decisions that are made in this part of the text lead to those kinds of details, you are learning a ton. So go and figure that out. Figure out, match everything up, figure out all the details. Book goes on and studies other cases. This is the potential step, where actually the step is more like a barrier, but a barrier with no backside. And then this is a potential energy barrier where you can have reflection off and also transmission through. And you can talk about what are called reflection and transmission coefficients. You can talk about tunneling and barrier penetration. Okay, so if you go and you look at the student learning outcomes for this end of chapter, or actually for all of chapter 5. So I put these on Canvas, and I showed you them in the directions video that I made a little earlier. So for chapter 5 on Canvas, one of the things is real world phenomena. So what is the connection between what really happens in nature and Schrödinger's equation models? And what's interesting here is your book shows you a couple of situations that can be modeled in a certain sense. And one of them is a really interesting piece of technology called the scanning tunneling electron microscope. If you can figure out how the scanning tunneling microscope is modeled by a potential energy barrier, then the honest truth is you've learned a lot. You really want to know, like, right, physics really is about how nature behaves. It's not math. All this stuff is really cool math and yada yada, but the point is how do you connect it back to the world? Like, so in this case, this quantum mechanics and this kind of like Schrödinger's equation stuff, that stuff's super old. The scanning tunneling electron microscope is a really modern instrument. 1986 Nobel Prize. It was probably made, I don't know, 10 years earlier than that, or maybe 20. I'm not sure, but Schrödinger's equation is a lot older than that. But the point is like, in some sense, people modeling with Schrödinger's equation predicted the engineering of the STM, the scanning tunneling microscope. So in a sense, because this exists, it's kind of experimental evidence. It's utilitarian, practical evidence that all of this Schrödinger equation stuff that's going on in chapter 5, that there is some real world truth to that, that nature does behave in this probabilistic way.